Math with Mr. Williams, example 1, describing shapes of distributions. Describe the shape of each distribution. So here we have the daily snowfall amounts. We see it's measured in inches. We see our number line 0, 1, 2, 3, 4, 5, and we see our dot plot. So in this case, when we're looking at this, we see most of the data are on the left, and the tail extends to the right side. So therefore, the distribution is called skewed right. All right, on to B. So we have passes thrown, we have the number of passes and the frequency count of that. All right, so the nice thing about this, even though it's not exact, it does make this pyramid here on our histogram. So the left side of the graph is approximately a mirror image of the right side of the graph. When I say approximate, it's close. So the distribution in this case, we're going to call symmetric. Math with Mr. Williams. Example 2, describing the shape of a distribution. The frequency table shows the ages of people watching a comedy in a theater. Display the data in a histogram. Then describe the shape of the distribution. All right, so let's go ahead and use our frequency table here, and we're going to go ahead and start making some bars over here in the histogram. So for ages 10 to 13, we have a frequency of 1. All right, for the ages of 14 to 17, we have a frequency of 3. And then for 18 to 21, we have a frequency of 7. And for 22 to 25, the frequency is 12. And then for 26 to 29, we have 20. Then for 30 to 33, we have a frequency of 18. And lastly, from 34 to 37, we have a frequency of 3. Okay, now that we've done our histogram, we need to draw and find our tail of the histogram story. So we can see most of the data is on the right-hand side, so the tail extends to the left. So this distribution is skewed left. Math with Mr. Williams. Example 3, choosing appropriate measures. You measure the speeds in miles per hour of 30 motorists. The results are shown in the table at the left. Display the data in a histogram using 6 intervals beginning with 31 to 35. And then B says which measures of center and variation best represents the data. So first things first, we need to display our data in a histogram. But in order to do that, we need to make a frequency table. All right, so now we're going to go and count out of this box how many numbers represent each speed. So from 31 to 35, if we go through our numbers here, we see we only have one number that fits. Then from 36 to 40, we only have 3. Now from 41 to 45, we have 5. Now from 46 to 50, we have 6. Now from 51 to 55, we have 11. And lastly, 56 to 60, we have 4. All right, now that we've made our frequency table, now we're going to go ahead and make our histogram. So the first one was from 31 to 35 as an interval, and our frequency was 1. So let's go ahead and put our bar on our histogram. The next one is 36 to 40 for 3. Then we have 41 to 45 for 5. And then 46 to 50 for 6. And 51 to 55 for 11. And lastly, 56 to 60 for 4. Now let's examine our histogram. We can see most of the data is on the right side, and if we draw a storyline, we can see that the tail is on the left. So therefore, the distribution is skewed left. So that means we want to use the median to describe the center and the 5-number summary to describe the variation. Math of Mr. Williams, example 4, correlation coefficient. Okay, so correlation coefficient is kind of revolving around this idea of 1 or 100% of the dots being on a line. So if we look at the first one up here, we can see that we can quickly draw a line that hits just about every single dot. So that would be a +1. So a +1 flow because it's also increasing or heading in the positive direction. All right, so if we look across the waves for its direct opposite, we can see that all the dots are on a line heading in the negative direction, giving us a -1 here, meaning that 100% of the dots are on a negative line. There is a negative linear relationship there. All right, so if we go down, we can see that we go from a +1 and we are working our way towards something called a 0. So we have 75 hundredths to 1. We can clearly see the dots are moving away from a line if we drew it down the center of the dots. But it is still a strong correlation. So if we go over the negative side of things, we can see it being negative and the fact that those dots are closely aligned to that line, giving us that -75 hundredths to -1 correlation coefficient. All right, so let's look at the next one on the left-hand side. We can see the dots are further away from the line. In fact, they are pretty good distance away. And so now 5/10 to 75 hundredths would be a reasonable number to put in there. Still a semi-strong correlation. Same thing can be seen on the negative side. And we see the dots are still pretty close, but at the same time, just far enough out. So here we still have a -5/10 to a -75 hundredths ratio because it is heading downward. So still a semi-strong correlation. And lastly, on the left, we have a 25 hundredths to a 5/10, or half the dots being close. Now this is one of the lower correlation coefficients as far as strengths. You can see these dots are definitely getting further and further from the line itself. And that's why the further away the dots get from that line, the lesser that coefficient number is. Until we actually get down to a 0, which I'll show you in a second after our last negative, being the same distance. Basically, you kind of see the flow still. It's heading in the negative direction. And again, a -25 hundredths to a -5/10. The numbers decrease and they work their way back to this 0. And what a 0 is, it's basically no correlation whatsoever. The dots are everywhere. There's no linear relationship. There's no relationship at all. There's no way to draw a line either going negative or positive.